Okay, so I was told that new people actually signed up this time compared to last time, and so I was told that it might be better to start from the beginning and hopefully review some of the material that we covered last week, but then go further than that and actually finish the whole slide deck. So maybe let me first introduce myself again. So my name is Mohammed Tariq. I'm a senior product engineer at PumasAI. And today I'll be talking about the connection between generative machine learning and nonlinear mixed effects modeling, and how that basically they are the exact same thing in the sense that they are trying to do the same thing. They often use the same kind of model structures, the same kind of algorithms. And so in many ways, they can actually be treated as the exact same thing. Even though many people working in generative machine learning may have never heard of the term nonlinear mixed effects modeling, and well, maybe not vice versa, because we all know about AI and ChatGPT now. But people working in nonlinear mixed effects modeling, they may not be familiar, let's say, with generative machine learning or the details of the kinds of models used there. So the goal of this talk is to hopefully connect these two fields together in your head, so that if you have a background in one of those two, the other field should become much more accessible to you, and the concepts would be much more familiar. So this is sort of the contents for today. So let's just jump straight in. So everything starts from the data. We need to understand the data that we are working with, and the data is at the center of every statistical analysis sort of exercise, at the center of every machine learning exercise. And the goal here, essentially, for both of these fields, actually, is to be able to generate synthetic data, meaning fake data from the model, that's indistinguishable in distribution from the real data. So what I mean by that is if you look at the real data and then you look at the synthetic data, you can't actually tell which one is the real and which one is the synthetic. And so that's sort of the ultimate goal here, is to try and get as close as possible to that objective. And for example, let's say we have the blue points here are the observations. So let's say we have this just y1 and y2, so two responses, for example. And so the blue points here are the observed points, and then we want to learn the distribution of these points. So let's say we learn this multivariate Gaussian that's shown here, or at least the contours of the log PDF or the log probability density function are all shown here. So let's say we learn this Gaussian or this multivariate Gaussian from the data, and then we use it to generate the red points. The idea here is that when you look at the red points and you look at the blue points, you can't actually tell them apart. You can't tell which one is the real one and which one is the generated one. And that's sort of the goal that we're going for here. And the same thing can be done not just for points or coordinates, but can be done for even pixels in an image. So a pixel is just or an image is just a high dimensional vector, basically, instead of just 2 dimensions in the previous slide. And so a lot of the generative machine learning models that have to do image generation, their goal is basically to learn the distribution of images, distribution of the pixels, the values of the different channels, the RGB channels in the pixels, such that they are able to then generate basically faces of people or any kind of images that they are trained on that would then look real or look close to real. So these are actually all people that don't exist, that were imagined essentially by a generative machine learning model. And in fact, there's a whole website dedicated to this called thispersondoesnotexist.com. So if you go there, every time you sort of visit the website, it will show you a photo of a person who doesn't exist. And so again, this is one way to at least visually check that, yes, we succeeded at our goal. And so visual checks are very important. And actually in pharmacometrics, visual checks are the primary checks that we rely on to make sure that we achieve this goal. And so in pharmacometrics, or when modeling time series or longitudinal data or panel data, which is data that, like let's say we have multiple subjects coming from a clinical trial. And each subject, we might have some drug concentrations over time, or measurements of drug concentration over time. And so we have this diverse data between subject variability, or each subject is different from the next subject. And the goal of the nonlinear mixed effects model often is to basically learn a model that's able to generate data that looks like this, that looks like the real data. And often the way we check this is using this visual predictive check. Because we know that two univariate distributions are equal or identical to one another if all of their quantiles are identical to one another. So if the first quantile of the first distribution is equal to the first quantile of the second distribution, second to second, third to third, not just the integers, also in between. But in the VPC, we only check 3 quantiles just to make sure that at least we captured the essence of the distribution of the data. And so we often check the median and the upper quantile and the lower quantile over time or over any kind of covariate. And we'll see how covariates are going to be handled in this context. And so the goal here again is to check that the quantiles or the observed quantiles shown by the black lines are close to the simulated quantiles shown by the bands. So often we do multiple simulations and take the quantiles of each simulation run, and then we plot a band for that. And so, but the goal essentially at a high level of a visual predictive check is not much different from this here, or this kind of visual check, where we look at those photos and we think, okay, those look real enough. And that's basically also the goal here, is to look at these plots and say, okay, this looks close enough to the real data. Now, the data structure that we have to work with is often hierarchical in nature and heterogeneous. So what I mean by that is, let's take longitudinal data as an example. So every subject, for example, from clinical trial data might have one or more response variables. So there might be some PK variable, like drug concentration over time, and then there might be some PD variable, which measures a specific quantity of interest in the body as well, that we would like to affect. And for each of those response variables, the PK and the PD, there can be one or more observations. And we often have a different number of observations for PK versus PD. But we also often have different number of observations for PK from subject 1 to subject 2 to subject 3. So the subjects may have varying number of observations. And so that's what I mean by first the hierarchy in the structure of the data, but also the heterogeneity in the structure of the data that we often have to deal with. And perhaps not different from that is in image data or scan data. Often every subject, again, can have one or more images or scans, perhaps from different angles or just different types of scans. And so, for example, a patient can have a CT scan and an MRI scan. And every image or scan can have many pixels or points. Some scans might have a higher resolution than others, depending on the practitioner taking that scan, and obviously CT and MRI may have different representations completely. And so this, again, manifests, or this heterogeneity of the data and hierarchy manifests in a very similar way. And images themselves can have different sizes and resolutions and so on. And so the reason we care about the data is because our goal, or the data structure, is because the goal at the end is to create a model or come up with a model that's able to generate data that looks like this data. And so we often have to match the structure of the data in the model. So for time series data, for example, we need a temporal model, and that takes time into account. And for spatial or image or scan data, we often need a spatial kind of model that takes neighborhood structure into account as well. So it's very important to keep the structure of the data in mind. So what exactly is a generative model? So let's jump into the details. So generative model is a term that's often used to describe probabilistic models in general. So any model that takes advantage or makes use of random variables to simulate new data. And so this is very generic. So let's take an example. So this is an example here of such a model. And often the way that these models are structured is using some variable called a latent representation or a latent variable. And here I'm denoting that by the letter eta. And so this eta is going to be some latent representation that's often modeled as a random variable. So this is not observed. That's just sort of our own mathematical construct that we came up with. And it's often modeled as a random variable here. And then once we sample eta, so for example, we can model it in this case as a univariate standard Gaussian or normal distribution. And then we can sample values for eta and then feed it into the next component, which is this parametric function. So a parametric function is just a function with parameters. Now, I'm not showing the parameters here just for brevity, but you can always assume that there are some parameters in this function. And so this here is a function of eta. So it just takes the value of eta from the previous step as an input, and then it returns a probability distribution for the response variable y. So for whatever y is that we care about, could be images, could be longitudinal data, could be just points or a point cloud. So often it returns a distribution. So in this case, for example, it returns a normal distribution. So this here is the function f, essentially. And the parameters of f would be things like this vector here, and this matrix. So those would be considered the parameters of this function. And it takes an input, this scalar or this univariate or value sampled from a standard Gaussian, and then it returns us a normal distribution for y. And so this is the second component of a generative model. So most generative models follow this kind of structure. In some cases, we don't have a distribution as an output of f, but we actually return, or the function f returns y directly, or returns the point directly, which you can think of it as a special case, where basically we have a distribution with a single point in its support. And the single point output is sort of a special case of the more general probabilistic output. So let's discuss some terminology. So the latent representation eta of the data point. Data point could be an image, could be some longitudinal data, data corresponding to a subject, could be anything. So this is slightly abstract here. But in general, eta is basically whatever your model is trying to generate. But the eta, the latent representation here is has some nice properties, which is that it's often low dimensional. And so, for example, if I have y here is 10 dimensional, I can maybe use eta with only 2 or 3 dimensions. And so this is nice because it can then be used for dimension reduction, which we will see in the next few slides. But eta is often low dimensional, or at least lower dimensional than the data is, or the dimension of the data. Eta is also often or always fixed length. And so what that means is, maybe not always, I'm sure there will be some exceptions, but in most cases, in the vast majority of cases, eta is fixed length, which means that even if y here is heterogeneous, so different subjects may have different number of observations, maybe some subjects only have a baseline observation plus 1 more, another subject may have 10 observations, some images may have missing pixels between them. We always can sort of map it back to a fixed length representation or a homogeneous representation for all of these data points. So that's a really nice characteristic or property of eta, is that it's a fixed effect. Eta is often modeled or almost always modeled as a random variable sampled from a parametric prior distribution. A parametric prior distribution is just a distribution, like in this case here, with some parameters. So the parameters would be the mean and the standard deviation, or the variance parameter in this Gaussian distribution. And it's called prior just because there's some connection to Bayesian, or there's a Bayesian interpretation of this. But it's basically just a parametric distribution for this latent variable. And the goal of this distribution is that we can then sample from it values for eta, which would then allow us to, so once we sample a value here, we can feed it into this one, and then allows us to sample values for y afterwards. So that's sort of the point of modeling it as a random variable. Now, a few names for this eta. In machine learning, people like to call it latent variable in a lot of literature. In some more recent literature, people call it the embedding, or the embedding variable. For example, in large language models, which is a generative model, you often hear the term embedding a lot, and it refers to this idea of a latent variable. You can also call it the latent feature, or in our field, we like to call it random effect. And I'm going to be presenting all this terminology, all these different ways to call the same concept, so that hopefully you come out, and then if you go see a paper and the paper uses this terminology, then you can easily connect it to what you already know. So if you come from machine learning, you're probably more familiar with latent variable or embedding. If you come from nonlinear mixed effects modeling or pharmacometrics, then you're probably more familiar with random effect. Now, eta does not have to be continuous. Eta can also be discrete. So it could be a latent representation that's discrete. And when it's discrete, it's commonly known as a cluster. And this is related to the common or the popular machine learning task known as clustering, because we can actually use it for clustering. But you can interpret this discrete latent representation or latent value as essentially a cluster for the data points. Now, the latent variable is often, or in this context, it's always per point or per subject or per image. So whatever the unit of data is that you want to generate, if it's an image, for example, then we have one latent variable per image. If it's like subjects, maybe potentially PK and PD within that subject, then we have a single set of random effects for each subject. And in our case, in the previous case where I just showed you a bunch of points, two-dimensional points, then the target here is just the two-dimensional points. And so eta would be per point in that case. But the prior distribution, the parameters of the distribution of eta, those are fixed for all the subjects. So those are not changing from one subject to the other. They're shared between all of the points or all of the subjects or all of the images, which would be this distribution here. Okay. So this parametric function f, so we discussed the latent variable and all its different names. Let's see what the names are of the function f here. So the function f in machine learning is often called as a decoder or a probabilistic decoder when it returns a distribution. So often, as I said, it returns a distribution, so then it would be a probabilistic decoder. And the idea is that it takes this latent representation, eta here, and then it decodes it from this space of the latent variable or the space of random effects to the space of the data. So it decodes it to something that lives in the same space as the data, or a distribution from which we can sample essentially fake data or synthetic data. So that's sort of the rationale behind this decoder. You can also call it a generator because, again, it can be used to generate data, or in statistics and NLME or nonlinear mixed effects modeling, we just often call it the data model or even the error model in some contexts. And as I said earlier, the architecture or the structure of the decoder function f must match the structure of the data because the goal is to generate data that looks like the real one. Okay, so let's talk about the parameters. So the parameters of the decoder and the prior distribution of the latent variable are shared between all of the points. So these are parameters that are not individualized, not per image, not per subject, but they're often shared between everybody. And these are just the model parameters. In pharmacometrics or nonlinear mixed effects model parameters or in hierarchical statistics. Those parameters are often called population level parameters because they're shared between everybody. But as I said, the latent representation itself is actually per subject or individual parameter or subject specific parameter. Now a subject here could also be an image or a point, as I said earlier. Now, often a subset of those parameters in pharmacometrics are often called, or in nonlinear mixed effects models, are often called fixed effects as well. So those are multiple different names for these parameters. In deep learning, all parameters in general are called weights, or often weights and biases. So if you see this term weights and weights and biases, they're not really weights of the points or like weights of people. They're just the parameters of the parameters of the neural network, basically, or of any kind of deep learning model. And so the term weights is used to refer to the parameters of usually neural networks in this context. So speaking of neural networks, so let's take an example of a generative deep learning model. What would that look like? So it sounds very fancy, but it's actually quite simple. It's the exact same model that we saw earlier, where eta could be sampled from a standard normal distribution. The only difference is we replaced the decoder. We replaced this function f. And we replace it with, again, a normal distribution like earlier. But so this is a specific example. Obviously, you can do whatever you want in these kinds of models. But in this example, it's a normal distribution. That's the output of f. And the parameters of the normal distribution, the mean and the variance parameters are themselves the outputs of neural networks. And so this is a neural network function with weights, with biases, with parameters. And those parameters here need to be tweaked and tuned and optimized such that at the end, the data looks like the real data. When you sample values for eta here from a standard Gaussian, so this is just some noise or some random values from a standard normal distribution, and then you pass it into a neural network, and then you get the mean here. You pass it into another neural network, you get the variance, and then you get the normal distribution for y. You sample from that, and then the hope is that by fitting or by training or by tweaking those parameters, we can actually get something that looks like the real data at the end. And so that's an example of a decoder that's often used in variational autoencoders, for example. So this is the exact decoder of the variational autoencoders, which is a common machine learning or generative machine learning model. Now, the latent variables in this case, or in the context of generative deep learning, is just a vector of random degrees of freedom. So often in pharmacometrics, we assign some meaning, for example, to these. But in deep learning, they have almost no meaning assigned to them or pre-assigned to them. It's just a bunch of degrees of freedom that the neural network can use in any way it sees fit, as long as at the end, the goal is to find a model that can generate data that looks like the real data. So if it was able to do this, great. And then we can look at the model that it learns afterwards and pull this neural network out and see if we do sensitivity analysis, if we try tweaking different values of eta, how does that affect y at the end? So often the behavior or what each latent variable does exactly is emergent behavior. It's behavior that we sort of try to learn about or discover or explain after the fact, after we've fitted the model. And these meanings are not sort of pre-assigned. But often the way that these models are fitted promotes sort of some level of independence or orthogonality between the behaviors, or rather the effects of these random effects or these latent variables. So often the first latent variable and the second might be doing something that's visually distinct, but that's not engineered into or exactly what they do is not engineered, but often the orthogonality or the independence or the distinctness of their effects might be engineered into the model or into the way that the model is fitted. Now, to contrast this, I'm calling it here a generative pharmacometric model, which often you would just call that a nonlinear mixed effects model or a population model, like a POP-PK model or POP-PK-PD model. And in this case, the decoder is often a mechanistic model. So it's a model that's maybe based on differential equations. It describes how the drug is absorbed into the blood, and then how it affects some sort of quantity in the body, like a PD variable. And so often there's a mechanism that the scientist or the modeler has sort of sat down and tried to come up with for this function here, for this decoder function. And this is often called also a scientific model. But for some contexts or for some cases, we are actually not able to come up with such a mechanistic model that makes sense, that's nice and compact, but also explains the data. And so often we have to resort to empirical models for data that may be difficult to easily come up with a mechanistic model for. And when you have a fully empirical model in the context of a sort of a nonlinear mixed effects model, that's basically a generative machine learning model. So machine learning is just a sort of empirical modeling rebranded in many ways. We just sort of come up with a powerful or a structure of a model that's very flexible, very powerful, that can capture the behavior of the data, and then we fit it, and then we try to make sure we don't overfit. But essentially, when you use a fully empirical model, you're not that far from using sort of, or basically you are doing some machine learning in that case. Now, sometimes we don't want to give up completely on our scientific insights and mechanisms, and maybe we know a mechanistic model that works in most cases, but and perhaps fits the data in many parts. But maybe there's one part that we suspect it's wrong or it's not very well specified. And so in that case, we can try to use an empirical component in a mostly mechanistic model, for example. And this is often called a semi-mechanistic model, which the rebranding of that these days is scientific machine learning. So if you have some component of your model that's empirical and some component that's mechanistic, then we often call this a semi-mechanistic or semi-empirical, I suppose, model. And so the structure of the decoder, or in pharmacometrics, the decoder is basically the model that takes in input the latent variables or the random effects, and then tries to give us a distribution for the response at the end, which could be a PK variable or a PD variable. Now, in a generative pharmacometrics model, the latent variable also has a meaning, and we try to assign it a meaning, as opposed to in deep learning. And the meaning is often a subject's deviation from the population typical value for a specific individual quantity. So let's take an example. So if the individual quantity is clearance rate, or how fast the body is getting rid of drug from the blood, then every individual might have a slightly different clearance rate. And so usually we model the typical value of clearance as a population parameter, or basically a parameter of the decoder. So this becomes the parameter of the decoder. And then for every individual, for every subject, we try to use this latent variable or random effect to express the deviation from the typical value. And so if you look at this, this could be sampled from a Gaussian or a normal distribution that has a mean 0, for example, and some variance parameter. And if this here is positive, then the exponential of a positive number is more than 1, and then the clearance will be some TVCL, which is positive, times a number that's more than 1. So this will be more than the typical value for this individual. And if this individual, or if another individual has an eta CL of a negative value, then this will be less than 1, and then that individual will have less than the typical value of clearance, or a clearance that's less than the typical value. And so basically, because of the way we used the random variable in the model, because of the structure of the model, we were able to assign a meaning to this random effect or to this latent variable. And then if we remain honest to this assignment, if we don't use eta CL in any part of the model, any other part of the model, then we hope that this basically meaning of the eta CL is actually respected when you fit the model. And so you can choose what meaning you want to assign depending on how you're using that parameter in your model. But of course, if you start using it everywhere, then it loses its meaning that you assigned earlier. And so In pharmacometric models and generative pharmacometric models, we often assign meaning to the random effects or the latent variables. And in this context, the TVCL, or the typical value of clearance, which also has a meaning assigned to it, is a population level parameter or a parameter of the decoder, part of the decoder function f that we described earlier. And the prior distributions parameters, so the parameters of the distribution or the prior distribution of this random effect here or latent variable are also going to be population level parameters. So those are going to be shared between all of the individuals. Now, besides assigning meaning to eta, we often also assign meaning to the prior distribution or the distribution of the random effects, and for example, the covariance parameter of the random effects. And the meaning we assign here is that between subject variability for a specific quantity of interest. And so if eta CL here had a covariance or a variance of maybe 3, then that tells us that there may be quite a bit of variability between the different subjects in terms of their clearance. And if it only has a standard deviation or a variance of 0.01, then that tells us that most of the subjects seem to have a pretty tight variance here. And so the idea is that even the variance of this latent variable actually has an interpretation. And so you'll see that the main difference between generative pharmacometric models and generative deep learning models is first the use of structure or more use of structure and scientific modeling in the pharmacometrics, but also the assignment of certain meaning to the parameters. Whereas in deep learning, it's a lot more sort of agnostic to the model structure. You just give it a very flexible model with a lot of parameters, and you hope it fits your data. And so there's some pros and cons to each of those approaches, but that's out of scope for today. But in essence, the fundamental structure of these models is the same. That's what I'm trying to hopefully convince you of by the end of this talk. So let's say we define the generative model. How do we go about sampling from that model? And so the sampling process from a generative model takes 3 steps, sometimes 2, but mostly 3 steps, which is to first sample a random value for the latent representation or the latent variable eta from its prior distribution. So if it's a standard Gaussian, we just sample some value from the standard Gaussian. If it's a uniform distribution between 0 and 1, we can sample a value from a uniform distribution between 0 and 1. So this is whatever distribution that we assigned. And then we take that sampled value and then we decode it, or we pass it through the function f, which has some parameters, and those parameters ideally would have been fitted before, so that your model actually doesn't generate nonsense, but generates something that is reasonable and looks like the real data. But even if it generates nonsense, you can still generate it, and it's still a generative model. So what the idea is to take the eta and pass it through this decoder function f, and then it outputs a distribution. So this will give us a distribution for y. Now this distribution is commonly known as the conditional distribution of y, because it's conditional on the value of eta. So this is the conditional distribution of the response y given the value of eta. And as I said, that sometimes this will just return a point, and if it returns a point, then you can just, that's it, the sampling ended here, that's the point that you're going to generate. If it returns a distribution, then we need to go to the third step, which is to sample a value from the conditional distribution. So this is often going to be a simple distribution, like a normal distribution for maybe unconstrained responses. If the response variable, if y can go from -infinity to +infinity, then this would be a normal distribution. If y is positive, then this could be log normal distribution or gamma distribution. So the distribution output of f should match the domain of the data as well, and the structure of the data. And the third step, as I said, is to just sample a value for y from its conditional distribution. Okay, so now that we know how to sample from a generative model, let's discuss fitting generative models. So how do we fit these models? Now, I'm not going to go into too much details, but I'm going to show you sort of the high-level idea. As I said before, the goal is to find the best values of the parameters of the decoder and the prior distributions, all of the population level parameters, all of the generative models parameters, such that we can generate data that looks like the real data. And we need to define a certain objective function value. And so we need to find the best parameter values by some definition of best, which is the objective function value. And so one very popular objective function value, both in machine learning and in pharmacometrics or nonlinear mixed effects modeling, is the marginal likelihood, or the log of the marginal likelihood. Taking the log when maximizing doesn't change the maximizer, because the log function is a monotonic function. So the log just allows us to describe it in an additive form rather than in multiplicative form. But in any case, we try to maximize this log marginal likelihood, which is also often known as the evidence in machine learning. And if we look at this, this marginal likelihood, this is the marginal likelihood for all of the subjects. Let's say we have n, uppercase n subjects here, or individuals. And now for each individual, we take the log of the integral of this here. And this term here is known as the conditional probability of y given eta. So this will be the probability of observing a certain response y. So let's say y is equal to 10. So this will be the probability of observing y equals 10 given the values of eta according to the distribution of y f of eta. So the way we would compute this is we take the value of eta for any specific value of eta, we pass it through f, we get a distribution here, and then we evaluate the probability density function of this distribution for the value yi equals 10, for example, or whatever the observation is here. So this is the actual observation yi. And we take this conditional probability, not for a specific value of eta, but basically we integrate out eta, or we take the expected value of this term here by sampling values for eta from its prior distribution. So that's the intuition here, is that you take random values from the prior distribution and you just take the expected value of this term here for all values of eta, or the mean, the sample average, essentially, asymptotically, for all values of eta. And that's the intuition behind it. So we don't usually compute it like this. So we have much more efficient ways to compute this or to approximate this. But intuitively, it's just the average conditional likelihood or the average conditional probability by sampling values from this distribution or the prior distribution of the latent variable. And this is a very nice objective function value in that it has a lot of nice properties in generative or when you're interested in generating data. It often encodes something called generalization performance, or it's a measure of how well your model generalizes to future observations given previous data. And so it has some nice properties, but that's unfortunately out of scope for today. But the goal of showing this is that I want to show you that this is the exact same objective function that's used in both training nonlinear mixed effects models, as well as training many, not all, generative machine learning models. There are other ways to train these generative models, but this is also a very popular way, even in machine learning. Okay, so I think this is now venturing into a new slide that we couldn't cover last week. But the third sort of thing you can do, so far we mentioned you can sample from a generative model. You can fit a generative model, ideally before you sample, otherwise you'll be sampling nonsense. But something else we can do is something here I call solving the inverse problem. And so let's say we already have a model that can generate data that looks like the real data. And so instead of using the model in forward or in the more traditional way, which is just to generate synthetic data from a random variable eta, so we sample eta and then we get a distribution for y and then sample from that distribution, we can use the model in reverse. And what I mean by that is given an actual observation y. So if I give you a real image, or if I give you a real subject, real data for a specific subject, can I then infer or figure out the best latent variable value, or eta star, that best represents this point? So what is the best latent representation in this latent variable space or in this embedding space that would then represent this real data point that I provide you? And so I'm kind of trying to use the model in reverse. And the way that this is often done is by solving an optimization problem and minimizing what I call here a dissimilarity function d. So dissimilarity is just like a distance function, or it's a function that tries to measure how dissimilar or how distant two objects are, or two quantities are. Now, the term distance in math has a very precise definition. So I'm using dissimilarity as a sort of more casual distance measure. And so d here, the idea of this uppercase d function is that it measures the dissimilarity, in this case, between the distribution f of eta, so that the output of the decoder, and between the real observation y that I gave you. So I gave you a real observation y, and then the model is able to generate this here. Given any value of eta, it can give me a distribution. If I can measure the dissimilarity between the distribution f of eta and the actual observation y, I can try to find the eta that minimizes this. So I can try to tweak eta, play around with eta to minimize this distance, and then until I get to the best possible value of eta, which I'm calling here eta star, that essentially represents or encodes or may have generated y. So one other way to look at this is that I'm interested in the most likely value of eta, the most probable value of eta, that may have generated this real observation y. And so if I plug in eta star here into this decoder, get a distribution out, sample from that distribution, the samples should come out looking very close to the actual observation y. So that's the goal here. And so we can solve this optimization problem for a specific choice of the function d. Now, in pharmacometrics, as well as in some areas in machine learning, not all models would do this, but in some models, you can define this dissimilarity function as this function here. And this might be familiar to some of you as the negative log of the joint probability of y and eta. So this is again coming from more Bayesian interpretation, or this could be the negative log of the PDF of the posterior distribution up to a constant. So the constant is left out here. But in any case, this is basically a dissimilarity measure, and I'm going to convince you that it is, between the distribution f of eta and the response y. And so if we look at the first term, this is actually the dissimilarity function. And for example, let's assume that f of eta here, so let's assume that this function f of eta here outputs a standard Gaussian, outputs a Gaussian that's centered around 0 and has a standard deviation of 1. And then if y here has a value of 10, for example, which according to a standard Gaussian is extremely improbable. So a value of 10 will have a very, very low probability according to a standard Gaussian, which means that this value here will be very close to 0. This value here will probably be a very large negative number, and then you take the negative of that, and this will be a large positive number. And so because the distribution f of eta and the observation y are very far from each other, then this has a high positive number, or it acts as a penalty, or it acts as a dissimilarity between the distribution and the observation y. Now, the second term here essentially acts as a regularization, so that in case y has a large noise term, maybe I know that all of the eta values tend to be around 0, and so I don't want to be picking eta star equals 1 million. And so this here acts as some sort of regularization to try and keep the values as close as possible to the mean or the mode of eta according to its prior distribution. But that acts as just some regularization, and this one here gives us sort of the main dissimilarity measure between the distribution f of eta and the actual observation y. Now, in case we have, for example, y is an outlier or there's a large noise component, this can come in handy by regularizing the optimization. Now, there is always a risk of overfitting here. So if, for example, we don't have this regularization term, or if we have a lot of random effects here, and we have maybe a few observations, and there's always a risk when we're trying to do this optimization, we may overfit the data point. And this overfitting in the context of pharmacometrics is actually something that we often measure and report, and it's reported under a different metric. It's called epsilon shrinkage. But essentially, epsilon shrinkage is trying to measure how much overfitting there is in this context here. But going beyond that in details is also out of scope for today. Now, this again is very familiar to perhaps some of you who are doing pharmacometrics or nonlinear mixed effects modeling, because eta star, when using this specific definition of the dissimilarity function, is called the empirical Bayes estimate. So this is what it's often called. In machine learning, they would just call this embedding, but in our field, we call this the empirical Bayes estimate, which again is the most likely value, or you can interpret it as the most likely value to have generated this real observation from the model. And in this optimization, we fix all of the parameters of f. So all of the parameters of the decoder, all of the parameters of the prior distribution, even this prior here of the latent variables, those are kept fixed. The only thing that we optimize with respect to is the random effects or the latent variables. Now, more generally in machine learning, eta star is called an embedding variable, or the embedding. And so again, you can pass in an image, for example, to many different generative models, or models that have this ability to be used in reverse, and then you can get the embedding of this image. Or you can pass in a text to something called an embedding model, or an embedding large language model, and then you get an embedding representation, or the best sort of eta star that may have generated this text, given the large language model. So all of these different generative models have some sort of idea that's very similar to this idea of eta star, or their own interpretation of it. I mentioned that in this optimization, the parameters of f and the prior distribution are kept fixed, which is very important. But also, one nice use of this inverse problem is that because of the dimension of eta, is often less than that of y. So let's say y is an image with thousands of pixels, but eta is only a vector of length 10. So the dimension of eta here is less than the dimension of y. And so we can use this inverse problem for dimension reduction, because essentially, if your model is able to capture each data point pretty well, that means that for each data point, you can also find at least one value of eta or eta star that sort of captures the essence of this point. And so I can then, instead of using this data directly in any downstream analysis, maybe I want to use it for some other machine learning task or some other sort of data analysis task. Instead of using y or keeping around the entirety of y, I can just keep around eta, which is a more compact representation, lower dimensional representation of the data point y. And this is often called dimension reduction or factor analysis in statistics. Or just feature extraction or automatic feature extraction, because you can think of those as basically latent features about your data that you were able to extract through solving the inverse problem. Now, the inverse problem can also be used to get a fixed length encoding of variable length data. So I mentioned that our data can be heterogeneous, and you can have different number of observations per subject. Working with heterogeneous data is often challenging in any sort of downstream task. If you want to use this data for anything to predict something else, for example, then you can actually use the random effects or the empirical Bayes estimates that you get from this encoding. And this process is often called encoding. You get this fixed length representation eta star of variable length data, which again, you can then pipe into some other machine learning task that only expects a fixed length or a uniform kind of input. Uniform in the sense that it has the same length. Now, if eta is discrete, this is an interesting case as well. So if eta here is discrete, so I'm assuming that we can do this minimization, for example, with gradient descent. So we can maybe find the gradient of this and then try to find the minimum point of this here. But if eta is discrete, not continuous, then we can actually, the most naive way is, let's say eta can be 1, 2, 3, or 4, is to just plug in all of these values here, plug 1, 2, 3, and 4, and then get the minimum value here, or find out which one is the minimum value. And that becomes your eta star, basically. And in this context, you can think of this as a clustering algorithm. So you can think of eta as a cluster. So we have 4 different clusters of data. And for every new data point that comes in, or for every new subject, I can solve this optimization problem or this inverse problem. And then for that subject, I can assign them either cluster 1, 2, 3, or 4. So this is basically the idea of clustering, or you can use this kind of model for clustering. So you'll see that there are many uses of a generative model when using it in reverse, not just when using it to generate data. Good. Now, the solving of the inverse problem is often called an encoding, or encoding the data, which is sort of the opposite of decoding, because we take the data in its natural domain or its natural space, and then we convert it or encode it to this lower dimensional, often fixed length representation in some lower dimension, most of the time. And so we can think of it as encoding the data. And in fact, the whole process or the optimization itself can be thought of as an encoder. So this function here is a function of y, because eta was just like eta is the output, basically. So we optimize with respect to eta, and then this is the output, which is the minimizer. But for every y, we have a different minimizer. And so you can think of this whole thing as just a function of y. And this here is essentially the decoder, or can be called a decoder, because it decodes y into the embedding space or the latent variable space. Rather, encoder. I don't know if I said decoder, but this would be the encoder, which encodes y into the latent space. Okay, so solving the inverse problem is often called encoding the data. Now, instead of solving this inverse problem over and over again, there's actually a common trick that's more popular in machine learning than in pharmacometrics. Although there's one paper, I believe, that came in the last few years that also tried this trick, which is instead of solving the optimization problem, you try to train a surrogate neural network to approximate this function g. So instead of doing this for, let's say we have a million observations y, instead of doing this million optimization problems or solving these million optimization problems, we can try to find an approximation of this function that's often a neural network with its own set of parameters. And this approximation just takes an input y, the data, and then tries to predict what the optimal value eta star is. So that's often used for big data, and it's more popular in the context of machine learning than in pharmacometrics. And so this is just a surrogate neural network that tries to approximate this encoder here. And often, actually, this surrogate model itself is what's called the encoder. So you can think of this as an approximate encoder as opposed to perhaps the more exact encoder when solving the optimization problem directly. But often this model itself, the surrogate model, would be called the encoder. And in this case, it just returns a single value eta star, which is the most probable value to have generated a certain observation y. Now, so here also that the optimization function itself, or the original function g of y, can be considered an exact encoder. But more commonly in machine learning, you'll find that the surrogate model is what's called the encoder, and not this optimization, because often people don't solve this optimization problem in machine learning. Now, surrogates can learn a point estimate, or can learn a single eta star, like we showed earlier, or they can even learn an entire distribution of eta values that could have plausibly generated y. So I mentioned the eta star has the interpretation that, so let's go back maybe here. Eta star has the interpretation that it's the most probable value, or it's the most likely value that may have generated the observation y. Now, maybe there's multiple such values. Maybe if my model has a lot of random effects or latent variables, and maybe not many observations. So maybe I only managed to observe the baseline observation or 2 points for a specific subject. There might not be just a single set of these random effects or values for these random effects that perfectly fit or explain the data or perfectly describe this data. And so in some cases, you may be interested in the entire distribution of the values that may possibly explain this response y. And this kind of distribution is more commonly and formally known as the posterior distribution. So the posterior distribution, the more casual interpretation of it, is all the possible values of the random effects that may have generated a specific observation y. And sometimes you can also train, instead of training a surrogate model that outputs a single point estimate eta star, you can also train a surrogate model that tries to approximate the posterior. And for example, it can try to give you a normal distribution approximation of the posterior, or some other approximation. If eta here is positive, then it can give you a log normal distribution approximation of the posterior, one that at least respects the domain, or a gamma distributed approximation of the posterior. And so it tries to approximate this posterior distribution of eta given y. And this kind of, or one way to do this approximation is using a technique called variational inference, which is common in statistics and machine learning. And when we have such an encoder that returns an approximation of the posterior, and not just sort of a prediction or an approximation of the mode of the posterior, which eta star would commonly be the mode of that posterior, or just a single most likely value to have generated the data, as opposed to samples or sort of an entire distribution of values. And so when we have an encoder, essentially, that generates an entire distribution or outputs an entire distribution that approximates the posterior, this would often be called a probabilistic encoder, or because we often use variational inference to do this, it's often called a variational encoder. So that's the main distinction between a variational encoder and a more deterministic regular encoder. And this whole concept of using a neural network often, or some kind of approximation mechanism to approximate this posterior here, instead of doing something more expensive like Markov chain Monte Carlo, so we can use MCMC, for example, to sample from this posterior, or if you're trying to predict the mode of the posterior, which you can use optimization to try and do that more exactly or more precisely. But instead of doing that, the idea of using a neural network or some kind of way to approximate this optimization or this MCMC process, this whole idea is often called amortized learning. And it's called amortized learning because we try to learn this function, which might take us some time, might be expensive to learn, but then we learn it once at the beginning, and then for every new data that comes in, we hopefully learned a model that's a lot cheaper to evaluate, or a function that's a lot cheaper to evaluate than to have to do an entire MCMC or to have to solve an entire optimization problem. And so this concept is often called amortized learning when you learn an approximation of the encoder, basically. And even though I am sort of potentially implying here, maybe unintentionally, that this is done as a post-processing step. So this is, I'm showing that maybe we fit the model first and then we solve the inverse problem. But in reality, often those are done simultaneously. So we can train the decoder and the encoder together. We can train the generator and the encoder or the amortized learning components simultaneously when we're fitting the model. But that's not too important. That's an implementation detail. So let's take some examples of a couple of popular deep generative models So again, sounds fancy, but the idea is that it's just a nonlinear mixed effects model that takes advantage of some neural networks. So it has quite a few parameters, which are all the parameters of the neural network. Maybe it has an architecture or a structure that you haven't seen before if you are not familiar with neural networks, but it's just a very rich or flexible nonlinear function that has a lot of parameters. And in this generative model here, so that's a popular generative machine learning model called a variational autoencoder. This model, the way it's defined is it has a standard Gaussian latent variable. So it could be 2, 3, 4, however many you want. But it's a standard Gaussian latent variable with mean 0, and the covariance matrix is the identity matrix. And then the decoder function f is a probabilistic decoder. So it returns usually a normal distribution for the output. And it's neural network based. And so it's literally the same model that I showed you earlier, which is this one here. So this is the exact decoder of a variational autoencoder, or a VAE for short, which is a popular generative machine learning model. And moving on, or going back to the slide. So I said the decoder is probabilistic. It returns a distribution, and it's neural network based. So the parameters of the distribution that we get are based, or the output of a neural network function of the latent variable. Now, the encoder in a VAE is often approximate, so we use this idea of amortized learning to try to approximate the posterior distribution. It's probabilistic or variational in the sense that we're not just interested in a single point estimate or a single value eta star that's most likely, or that could have most likely generated the data, but we're interested in entire distribution and an approximation of the posterior distribution. So it's an approximate, uses a surrogate model, but it also tries to predict or to approximate the entire posterior. And it does this again with a distribution whose parameters are defined by neural networks. So in a very similar fashion to the encoder, but here the target is to try and approximate the posterior, or the goal is to try and approximate the posterior, let's say with a normal distribution whose mean and variance parameters are themselves defined by neural networks. And so if that's your model structure, that's basically what a variational autoencoder is. Now, a normalizing flow is another really nice generative model that my colleague PumasAI, Lorenzo, has used in a very nice way, and he presented a webinar about it a few weeks ago that should be on YouTube. But it's basically just another generative model that has some nice characteristics, but at the core of it, it's just a latent variable. Again, that's a standard Gaussian, which has mean 0 and covariance matrix here as the identity matrix. And the decoder in this case is actually deterministic. It doesn't output the distribution for y, it just outputs a value for y directly. The main catch here is that the decoder has to be an invertible function. It has to be a function that we know how to take its inverse. And there's a whole class of neural networks that are called invertible neural networks that can be used for this purpose. But any kind of invertible function will work. Now, the fact that it has to be invertible necessarily means the number of inputs, or the number of dimensions in the output, and the number of dimensions in the latent variables or in the input have to be the same. So in many ways, the normalizing flow can be somewhat restricting in that sense, but it does have some nice properties and some very nice uses. But the number of inputs and outputs need to match for the decoder. But the decoder is deterministic. It doesn't output a distribution, and it's an invertible function, often based on neural networks. Now, the encoder in this case is exact. We don't need to approximate it. And it's also deterministic. So for every y, there's a single value eta star, not a whole distribution. And in fact, it's actually the inverse of the decoder. So I mentioned that the encoder is invertible. The exact inverse of that is the encoder. And it's exact because we don't need to approximate the inverse. We can just compute it because we have the definition of the function and we know how to invert it. So that's called a normalizing flow. The nice properties about a normalizing flow is you can evaluate things like the probability density function, and it's easier to fit than some of the other models. And so it has its really nice use cases, even in our field, as demonstrated by my colleague, Lorenzo. Now, for the rest of this, or most of the rest of this talk, how am I doing on time? Okay. For most of the rest of this talk, I'm going to be giving an example using a simple multivariate Gaussian that's maybe it looks simpler than it really is upon first sight. But let's see how we can work with this. So in this case, I'm assuming that I have some data generated from a simple multivariate Gaussian. And this multivariate Gaussian has a mean of 2, 2, or a vector here with length 2 and values 2, and has this covariance matrix. And so that's those blue points here that you see. And again, the goal is to be able to learn the distribution or a generative model that then we can use to generate the red points, such that the red points and the blue points look identical in distribution. When you look at them, you can't tell which set of points is the real and which one is the fake. So how are we going to do this? Just before we do this, maybe to add some context, you can think of each of those dimensions, y1 and y2, as maybe 2 response variables like pk and pde for a specific point in time, such as baseline. So you can think of this like we only have a single observation per subject. Just to add some context, we're going to show how we handle or how we deal with time series data more properly after this example. But just for some context, let's say that we have only a specific point in time where we took the measurements, and those will be y1 and y2. Alternatively, they can be the same response variable, for example, pk, but at 2 different points in time. But those are all the same points in time for all subjects. So all subjects got measured at time 0 and time 20. And so that's what we are seeing here. So just imagine that's what we're seeing here, just to add some more context to this. But again, we will see how we can handle time series data more properly in the next few slides. Now, we could just fit a multivariate Gaussian. So we could do exploratory data analysis, plot the data, look at it, and sort of see, okay, this looks like a Gaussian. I'm just going to fit a multivariate Gaussian. And that's doable, and we can do that. But I'm not going to do that today, because that would be boring, but also that would prevent us from exposing some interesting insights or structure about the data that we have. And so instead, I'm going to propose this alternative model. And this model might look very different from the previous model, from the multivariate Gaussian, but I'm going to convince you that this is actually the exact same model, just written differently. It's the exact same distribution at the end. And so here we have this latent variable eta that was not observed, that has a normal distribution with mean 2 and standard deviation 1. And then we take this and we pass it through our decoder function f. That the decoder function f basically multiplies eta by this vector. So eta is a scalar in this context, so it's the number. You multiply it by this vector to get the mean of this distribution. And then we have this residual variance for this distribution that then we can sample from. And so this model here, this generative model, is basically a multivariate Gaussian, the exact same multivariate Gaussian in disguise. It's just not very obvious when you look at it for the first time. But to convince you that it is, actually before I convince you that it is, let me write it in a slightly different way. So here I just remove the mean value of this y and sort of centered y and called it epsilon. So epsilon here would be the residual, essentially. And then it has the same covariance matrix, but it has a mean of 0. And now y is what used to be the mean. So this mean was taken out of here plus epsilon. So y is now a deterministic function of eta and epsilon. Epsilon is sampled from this distribution. Eta is sampled from this distribution. So this is just another way to write the exact same model that we had previously. Now, let's take a look at this distribution and try to reason about it. So this here is a Gaussian, or a normal distribution. This is a normal distribution. And so if in probability, it's well known that if you take a normally distributed random variable, and then you multiply it by a constant, this output here, or this outcome of this, or the product here, will also be normally distributed. It will have a different mean and different covariance, but it's also normally distributed. And then if I take a normally distributed random variable, like this one, and add it to another normally distributed random variable, then this will also be normally distributed. So two normal distributions, you add them to each other, or the variables are normally distributed. If you add them to each other, you get essentially the output is another normal distribution, or another normally distributed random variable that has perhaps a different mean and a different covariance. And so that's common knowledge here. So we know that y is going to be normal or Gaussian. And I'm talking about y meaning the marginal distribution of y, not the conditional distribution of y. So I mentioned before that this here is often known the conditional distribution of y, conditional on a specific value of eta. But what I'm more interested in here is the marginal distribution of y for all possible values of eta. So if I sample eta, plug it in here, and then sample y, repeat this many, many times, the kind of data that I get at the end, or the kind of simulations that I get at the end, their distribution is known as the marginal distribution of y, because we are sampling eta and not fixing it in this context. Okay, so we know that y is Gaussian. So that's first point, check. So the marginal distribution of y is Gaussian. Now, if we try to take the expected value or the mean of y using its formula, it's just this times the expected value of eta, which is 0, plus the expected value of, expected value of eta is not 0, it's 2. So 2 times this is going to give us that. And then the expected value of epsilon is 0, right? So this here, the expected value of y is exactly this vector here. And then if we try to find the covariance matrix of y, using, again, common sort of formulas in statistics, it's basically this vector here times the variance of the random effect or the latent variable eta times this same vector transposed, and then we add to it the covariance of this. So that's just a standard way to calculate the covariance of a linear function of random variables. And so if you do this here, this is just going to be this exact matrix. And so it's a Gaussian with the same mean and the same covariance matrix as the original data distributed or data generating model that we had, right? So it's the exact same distribution. It's just written in a different way. It's written in a way that exposes more structure, essentially, and it's written in a if you like, in a generative model way, or as a generative model. So this is literally the exact same distribution as a data generating multivariate Gaussian, but although it looks a lot different. Now, another name for this, if you noticed, the title of these slides was basically linear mixed effects models, because those are basically this is the structure. If I just generalize the parameters here, so instead of 2, I had 2 here earlier. If I make this a parameter theta, instead of 1, I make this a parameter omega. And now eta could be multidimensional. It doesn't have to be a scalar anymore. And then instead of the diagonal matrix with 0.2s on the diagonals, I have sigma. So if I just rewrite the same model, but using parameters instead of hard coding their values here, I get the canonical form of what's known as a linear mixed effects model. So that's just a linear mixed effects model, which happens to be, as I said, identical to just a regular multivariate Gaussian, but exposes more structure. So again, this is just the same as this here, this model, but where I substituted the numbers with parameters. And now this is a more general model family, essentially. Now, the goal with linear mixed effects modeling is often to find the best parameters, the best theta, the best omega, the best sigma, and the best z, such that the data at the end that you generate from this model looks like the real data. And in this case, I'm assuming that eta is m-dimensional and y is n-dimensional, where m is commonly less than n in this context here. So this, again, is a very famous model structure called a linear mixed effects model. Now, let's reparameterize things a bit. So actually, this model would be, in general, locally non-identifiable unless we have some more restrictions on z and sigma, usually. And also unless we make the number of random effects or latent variables less than the number of responses. So m has to be less than n. And yeah, at least if sigma here is, yeah, it has to be less than n. But in any case, so to make the model identifiable, I'm going to impose some more structure here. And hopefully, as we're doing this, I'm going to convert it to another model structure or another canonical form of a model that's also a very standard generative machine learning model. And so here I'm going to make sigma a diagonal matrix. I'm going to assume that this sigma here is diagonal. And I'm going to assume that omega is the identity matrix. So here's the identity matrix with size m by m. And this might seem like a very severe restriction, but keep in mind that we are multiplying eta by z, and z has no restrictions. And so the omega could be essentially absorbed by z in this case. And so you don't actually lose generality by doing this. But let's assume that we have these additional restrictions in place. So sigma is diagonal, and omega is the identity matrix. And we still have our theta here, which we can keep for now. But then let's say we actually also center eta. So the random effects here, or the latent variables, instead of being centered around theta, we want them centered around 0. And then we just add eta plus theta here. So we make this centered around 0. And then before we multiply it by z, we just add the value of theta before we do the multiplication. Now let's do some more refactoring and renaming here. So if we expand this, basically, and then if we also rename z to w, and rename z times theta to mu. And so what we end up with here is, this here is essentially z times eta, and this is z times theta, right? So if we just rename things a bit and expand the multiplication, we end up with this alternative model structure, model representation, where we have a standard Gaussian random effects or standard Gaussian latent variables, and then we have this linear or affine function of eta of the latent variables with some parameters w and some parameters mu. And mu here has the same length as y, and w here would be the length of y, or n times m, n by m matrix. And we mentioned that sigma is also often a diagonal matrix in this context. We applied this restriction earlier. Now, exactly this is the canonical form of a generative machine learning model known as probabilistic principal component analysis. So it's related to principal component analysis, but it's done using this probabilistic modeling approach. And that's, again, a generative machine learning model. It's very simple. It has this canonical structure, and it can be seen as just a reparametrization, essentially, of a linear mixed effects model, right? And so hopefully that helps drill in the concept that mixed effects modeling, generative machine learning are literally doing the exact same thing, even have the same model structures, give or take, with some reparametrizations. So in this context, also, sigma is diagonal, or even sometimes we just fix all the variances on the diagonal to the same value, but you don't have to. It can just be a diagonal matrix. And also in this context, m, the dimension of the latent variable, or the random effect, is less than n, which is the dimension of y, or the output here. So this is two-dimensional. This could be one-dimensional, for example. And this is often the most popular use of this probabilistic principal component analysis, is in dimension reduction or factor analysis, because we are solving the inverse problem. So even though it's a generative model, but our primary interest in this case is not generating the data, but rather solving the inverse problem once we have the generative model, and then using that for dimension reduction. So let's take an example of that. What would that look like? So I took 4 of the blue points that we had earlier, and essentially what I did is I solved the inverse problem. I actually minimized the dissimilarity that I showed you earlier. I solved the inverse problem, found what eta star is, and then I took the eta star and I plugged it back into the decoder f to take me back to the space of the observation. So I wanted to be able to plot some kind of representation of this eta star next to the data. And so by plugging it back into the decoder, I got something that lives in the same space as the y. And then this here is a distribution, because it's a probabilistic decoder. And so I just took the expected value of this decoder. Now, this is what we commonly call the individual prediction, or IPREDS, in the mixed effects or pharmacometrics literature. And so basically, I just took the IPREDS of each of those points. And then I plotted it. And so I have an arrow here that goes from the real observation, the blue point, to its IPRED, or to the value of the expected value of f of eta star. And so you'll see that this here is dimension reduction. You can see it in that at the origin, when eta star equals 0, basically you get this point here. But then if you go up on this line, then eta star, or if you increase eta star to more than 0, then you go up on this line. If you make it less than 0, you go down on this line. So it is literally moving along one dimension. So this is one dimension. It's embedded in 2 dimensions, so we can visualize it or plot it embedded in 2 dimensions. But it is just one dimension. It's a single line. And so by changing eta star, I can go up or down this line, essentially. And each of those points, you'll see that it's mapped to a point on this line. And you'll see that it's not exactly sort of projected, so there is a slight angle here. And this angle is what we commonly call in pharmacometrics as eta shrinkage. So this is eta shrinkage visually, basically, or visual representation of eta shrinkage, where we are typically trying to move closer. And this is due to the regularization term that I said we have earlier, is we typically try to move closer to the values of eta that are more likely. So we know most values of eta tend to be around here, and so we try to move a bit closer to that. And to make it more visible, I actually plotted more points. And so you'll see the further away the point is, the larger the noise component, the more likely that this observation could be an outlier, the more the effect of shrinkage is visible. Whereas close to the center here, you'll see that it's almost orthogonal, almost like regular PCA, where we're just projecting it on the line. But here, it's trying to also move it a bit closer to the origin. So that's a very simple sort of exercise that hopefully demonstrates that linear mixed effects models and probabilistic principal component analysis models are the almost exact same thing, just reparameterizations of one another, and also demonstrates some of the concepts that we can solve the inverse problem to do dimension reduction, and also demonstrates that the like you can write your model. Sometimes there could be different models or different representations or different ways to write, perhaps even the same model or the same data generating distribution. But writing it in one way can expose more structure, allows us to use it in more interesting ways than just writing everything as a multivariate Gaussian with a full sort of dense covariance matrix. Okay, so that's the end of this exercise, and the rest of this, or the next topic, I suppose, will be conditional generative models. Now that's, again, another fancy term that machine learning people like to use, but what it refers to is just the fact that we can actually have covariates in our model. So whenever we have covariates in our nonlinear mixed effects model, so far I haven't introduced any covariates, but whenever we add covariates, then it becomes a conditional generative model. And the condition here is basically the covariate. So it's another name for the covariate. It's the condition. And so here we can have, again, some latent variable or latent representation eta, and then the decoder function, instead of just taking eta as an input, it also takes some covariates, which could be, for example, baseline covariates. So these could be things like weight, sex, age, etc., height, or it could even be sort of an input from another embedding model. So like you can take an image and then solve the inverse problem for the image, get some fixed length representation, and then feed it here as a baseline covariate, right? So it could be a baseline image. And so this could be also coming in from another sort of dimension reduction exercise. But the idea is that it's just a bunch of a vector of numbers that you can input here to this decoder. And then your model becomes a conditional generative model, or which is the covariate model, or a covariate-based model. Now, time is a very special covariate as well. So often we are interested in modeling data that changes with time. That's a time series. And so in that case, we can also have time here as an input. And it becomes, like you can think of time as this special covariate that we also condition on. So we're not interested in modeling time itself, but we're interested in conditioning on time. And then we also have time here being a property of the output that we get. And so often y would be observed at only a few finite time points, 3, 4, 5 time points. We can't observe it for all time points. And so we can use those, whatever time points that we have observations for, we can plug in the value for time and then use it when fitting the model. But then once we have the model that has time as a covariate, we can now use this model to generate data for any kind of time point. So we can use it to generate data for any in-between time points, future time points, past time points. So if you're interested in predicting the future or simulating the future, you can have future time points. If you're interested in predicting the past, I suppose, or figuring out what may have happened 100 years ago from observations that we have today, maybe some historians or archaeologists might be interested in that, then you can also take time backwards and figure out what's the model trying to tell you there. Or it can be in between different observations. But the idea is that this is a time-based model that we can then use when generating data in any way that we like, or by substituting values for time that may not have been in the observations. That's obviously also true for baseline covariates. You can experiment. So if you have one of the covariates would be, for example, the dosing regimen or the amount of dose. And so once you fit your model with a certain observed value for this covariate or realized value for the dose, then you can experiment. What if I change the dose and do all sorts of what-if analysis or counterfactuals based on that. Now, in images, for example, you could think of this covariate as the style of the image. So I can train a generative model for images on human, like faces of people that could be captured from a camera. And then I can train it also on images coming from an animation, for example. And so there is actually a common, I think, website where you can give it your photo and then tries to learn the empirical Bayes estimates or the embedding, and then changes the style to an animation style. And then it tries to generate an image for you that would be an animation style. Right, so you can think of this as the style of the image, which can be either a real image coming from a real camera, or it could be an animation or an image coming from a certain animation, for example. And then we can, again, find the empirical Bayes estimates for a specific observation, which is a real subject or a real photo, like a photo of yourself, for example. And then given this random effects or given the embedding, I can start experimenting. What if I change the style to an animation? What would I look like if I was part of an anime or an animation? And that would help you answer that question, right? So that's a more maybe fun use of these covariates. But again, it is just a covariate, right? So it could be dose, it could be an image style, it could be anything you want it to be. Now, often in pharmacometrics, we also have a time-varying covariate, which is often it's just a function of time that's not fitted. It's a function of time that's user provided or provided by us. And often we only have, again, observations at finite points in time, or a few points in time for each subject. And so we usually just interpolate or extrapolate before we feed it into the model. So we for example, do stepwise interpolation and extrapolation, and just feed it as a function of time that's not really fitted, that doesn't have any parameters. You just input it directly here as a time varying covariate. Now, you can imagine also if you have a bunch of images over time, or a video, which is another word for it. So just a time series of images or a time series of scans, you can get the embedding of each frame or of each of those images, and then you can make a time varying covariate out of that. And then you can feed that into your pharmacometrics model, for example, and see if you can use any of the features extracted from the images to predict certain PD quantities or PK quantities that you may care about. So there's a lot of interesting work to be done here as well when using images as an input. But we can also use images as an output. I think if you have this, if you imagine this as the embedding, so if we're trying to generate the embedding, and then we can decode the embedding and generate images, we can also do it that way. And so once you sort of see that, generative machine learning, whether it's images, text, or data, or just numerical data, time series data, which is what we often call just nonlinear mixed effects modeling, are the exact same thing. You can come up with all these creative ways to plug them in or mix them together. So I can have a neural network in this F here, or part neural network, part mechanistic model. I can have a neural ODE, for example. I can have anything that I want in this F here. And it's really just sort of going back and forth along that spectrum of, are we doing full machine learning, are we doing full scientific modeling, or anything in between, maybe scientific machine learning, in the presence or in the context of having random effects. So we still have random effects, we still have latent variables, which makes this a generative model. Okay, so the final couple of slides. I think I took too long this time round, but hopefully it was useful. But finally, I want to conclude with a one-compartment PK model that's very familiar to a lot of people here. And hopefully, now that you've seen what you've seen, you should be convinced that this is just a generative model, or it's a conditional generative model. And so the latent variables would be often the random effect for absorption, the random effect for elimination, and the random effects for the volume of distribution. And they're given some normal distribution here for the between subject variability, which is just another word, or another word for the prior distribution of the latent variable. And the between subject variability, or the distribution of the latent variable, the random effect itself, has a parameter omega square. That's a population level parameter that needs to be fitted. And we have one of those for every one of those random effects. Then the decoder in our model is basically the entire structure of the model. So it's everything up until here. That's called the decoder. And so we combine the population level parameter, or the typical value of absorption rate, with the random effect for absorption. We combine the typical value for elimination rate with the random effect for elimination, and the typical value for volume of distribution with the random effect for that. And those would be population parameters again, or parameters of the decoder that we need to fit. And then here, this is the initial dose given at baseline, and this is actually the analytic solution of the differential equation describing a one-compartment PK model. So I just wrote the analytic solution, but you can imagine this could also be just solving a set of differential equations, which the differential equations themselves may or may not have a neural network. In that case, they might be called a mixed effects neural ODE, or a generative neural ODE, if you like. But here I'm just solving it analytically because it's easy, or it's possible to do that. And you'll see that I have two covariates. I have the dose and I have time also here as a special covariate. And then this, if I solve this function or evaluate this function, it gives me a function of time that I can then use as the mean of the normal distribution, or the output of the decoder F. So this here is the output of the decoder, where it has the mean of C of t here, and it has a variance parameter, sigma squared. That's another population level parameter that doesn't change with time. And as I said, this here would be the output of your decoder, and together with all of this is that's your decoder function. And then that describes the distribution of y at a specific point in time t. So hopefully you can see that this is a generative model. Now, as I said, C is just the drug concentration at time t. D is the dose administered, which is usually a baseline covariate, or at least in this context it is. Those are the absorption, elimination rates, and volume of distribution after applying the random effects, and each of them has a typical value and a random effect, or a latent variable. This is the observed response, or for example, drug concentration, and this is a population parameter that describes the variance of the residual error, which is the same for all time points. And so these are additional population parameters beside the previous population parameters here. So both of these sets of population parameters need to be fitted. And this concludes my talk about generative models and nonlinear mixed effects models. And again, hopefully we can walk away from this convinced that indeed they are the exact same thing, and that it's nothing very far or very different from what we have been doing so far. Whether what you've been doing is generative machine learning or what you've been doing is nonlinear mixed effects modeling. So I'm glad that this time I wasn't disconnected when I came for questions. And that means we actually can take questions. So if you have any question, please post it. So maybe let me go through these comments quickly. So are there any machine learning algorithms that are far away from NLME? So often a lot of the, if you're referring to generative machine learning algorithms, there are some generative machine learning algorithms that use a different objective function value, for example, when fitting the model instead of the marginal likelihood, and use a slightly different definition of the encoder as well, or a different way to define the encoder. But they are all trying to do the same thing, roughly, generative machine learning and nonlinear mixed effects modeling. Now, machine learning as a word or as a term is very wide, or it's a very big umbrella that might, it's not just about the generative part of it. So this is a much larger sort of umbrella that might cover other kinds of models, yes, that are not nonlinear mixed effects models. But in the context of this presentation, I'm referring to generative models and nonlinear mixed effects models. Any questions? I'll give people a few seconds, and if nothing is typed, then I would like to thank you for your attention, and hopefully you got some insights. Are there any mechanistic encoders? Good question. Not that I know of, to be honest. Often it's difficult to come up with a mechanism for what the possible or the best possible value for the random effects is given a certain observation. You can think of solving the optimization problem as the closest thing to that, because it's using the structure of your model, the encoder itself, the mechanistic encoder to try and, decoder, mechanistic decoder, using it to try and find or do the encoding. So that would be the closest thing to that. But I don't know of any kind of model that tries to reason about the mechanism for generating the random effects. Can we invert the numerical integration of an ODE? Possibly. I guess you can just. I don't know, to be honest. I need to think about that one. Invert the numerical integration of an ODE. It might be possible if your function, for example, is invertible. So there are some invertible flows and things like that. So it might be possible in some contexts, yes, for some ODEs. Not every ODE might be invertible, though. Okay, so Luke is here, my colleague, I believe, is also attempting to answer. So great, I'm glad people liked the presentation. So with that, again, if you have any questions, feel free to reach out to me, and we can maybe chat some more across or over email or some other venue, maybe on a call. But with that, I'm going to conclude today's webinar, and I'd like to thank you all again for your attention, and sorry for the inconvenience last time, and the technical issues. That I hope we compensated you for that, at least with information. So thank you.